Okay, well, I'll just go and just say this class is gonna be a pretty interesting class. I know I say this every time, but I guess the first part we're gonna talk about Pascal's triangle, which I will say is not completely relevant to beginner contest math, the title of the course, but I think it's a very fun, I guess, very interesting part of combinatorics that often, when you're more interested in this topic, it's easier to learn. And I guess it also kind of show how a lot of things are all connected within this field of math. And so hopefully after this class, you'll be a little bit more interested in combinatorics. All right. So last class, we did introductions to like permutations, combinations, like the n choose k or something choose another number, that kind of notation, the definitions and some of the problems. And if you recall, one of them was the one on the grid, where you had to go from like point A to point B, using like only going up and right. And we talked about this waterflow method, where you have like 1, 1, 1, 2, and like essentially it's the Pascal's triangle on its side. And I guess the main idea of Pascal's triangle is that it has all of the I don't know what I should call them. Their technical name is binomial coefficient, but you could think of them as just this row choose column. So this is called row 0. This is row 0. This is row 1, and so on. And then the columns would just be like the number within the rows. This is column 1 for row 0. This is column 1 for row 1. This is column 2 for row 1. Actually, that's subtract from that. I indexed everything wrong. Essentially, this is 0 choose 0. And then this is like 1 choose 1. Sorry, 1 choose 0 and 1 choose 1. And etc. So this is 2 choose 0, 2 choose 1, 2 choose 2. 3 choose 1, sorry, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Okay. I guess I will mention that anything choose 0 is equal to 1. You can probably see in the triangle. But this in itself isn't very interesting. We're kind of just listing out these values that are all a little bit disconnected in that they're currently only defined as something choose another number. But I guess the most interesting part of Pascal's triangle is that for every single term, let's say we choose 56, always equal to the sum of the two terms directly above it. So 56 is 21 plus 35. For example, this 210 here is 126 plus 84. And so you can like recursively define this triangle so that if you start with just, let's just say a shell of ones, so you basically have a 1 at the beginning and end of every single row, like so on. As you can see, it's like this part right here. This is like your beginner, and then fill in the rest by adding the two numbers above it, and then you'll just get exactly this same thing. Notice that like 1 plus 3 goes to 4, 1 plus 4 goes to 5, then 1 plus 5 goes to 6, and so on. And you can check every single number here. It does satisfy this property. And so why is this the case? Okay. The main idea here is that, not this, that I talked about last time, it's this, where here we have our first, identity for our combinations that has not come up before and probably won't in the future either. But it's pretty cool. It says that n choose k is n minus one choose k minus 1 plus n minus 1 choose k. So if we unpack, this refers to like the kth term in the nth row, right? I'm not going to write that down, but this is what this means. And n minus 1, k minus 1, this refers to the k minus 1 term in the n minus 1 row. And similarly, this is the kth term in the n minus 1 row. And so we have, if we just take an example, say n equals to 3, and k equals to 1. Then we have 3 choose 1 equals to 2 choose 0 plus 2 choose 1. And of course, this is 3 equals to 2 plus 1, or 1 plus 2. And if we look on the triangle, 3 choose 1, this is equivalent to this position right here. 2 choose 0 is this one here, and 2 choose 1 is this one here. So we have the 1 plus 2 equals 3. And so this is simply just a fancier way to write the condition that every element is the sum of the two elements above it, like so. And the observation that this holds for everything in this triangle is in itself not enough to completely justify that this is true. But you just know that you can use algebra. It's pretty simple actually to show this is always true. And you just go back to the definition for a combination, which was from last class, with it's n factorial over n minus k factorial and k factorial equals to n minus 1 factorial, and so on. It's kind of long to write. But the idea is that you can write this out algebraically and solve it. And it'll be a true equation, true statement, whatever. But in combinatorics, and this does come up with a lot, oftentimes the most more elegant, easier to understand proofs of these kinds of concepts is through something called a bijection. Okay, and a bijection is simply just equating two things that are, it's essentially just saying like two things have the same number of terms, or in combinatorics, it's counting the same quantity in two different ways. And so to illustrate this, consider what n choose k means. This is the number of ways to choose k people out of a total of n people, right? So this is n minus 1 choose k minus 1. This is the number of ways to choose k minus 1 people out of n minus 1 people. And this is the number of ways to choose k people out of n minus 1 people, right? So I'm telling you that this is, that these are both the same, like a number of ways to count how to choose k people out of n, right? So I guess, can someone, or I'll think about it, can you come up with a scenario or maybe explanation as to how the combination of these two, or the sum of these two combinations, can represent choosing k people out of a group of n? How does this sum of these like represent like a situation or scenario that's identical to this? You don't have to come up with an answer, I just want you to think about it for a little bit and see if you can focus on it. Okay, well, hope you thought about it. The idea here is that let's start on the left side. Let's just say that we have a group of n people. Well, let's say this n represents a group of people, right? And we want to take out like k of them. Right, this is just left. It's pretty easy. Now, consider what happens if we just choose a random person from this group of n, okay? So let's just say there's this one random person, R, and then we also have the remaining n-1 people, okay? Let's just say it doesn't matter who this random person is, just know it's just a random person. And now we want to do the same thing where this entire group, this is called n. So when you put R and n-1 together, they're just the original group of n people. Okay, and now we want to consider what this k-1 and k mean. Well, let's just say if we want to choose k people from this group of n, this random person can either be chosen or not chosen. Those are our two cases. So first, let's consider what happens when this random person is indeed chosen to be in this group of k. Then we have n-1 people remaining to choose from, and there are k-1 more people to choose because one slot's already taken up by the random person. So what this means is that we need n-1 choose k-1 different ways to fill up the remainder of that group. And this next term, n-1 choose k, this refers to when this random person is not part of that group of k that we are going to choose. In that case, we can just ignore them. And now we need k people from this group of n-1 in order to choose everyone that we need. And so that accounts for this term right here. And since there are only two scenarios that are possible here where the random person is either chosen or not chosen, this means that this is a complete, I guess, description of our situation. And since both of them describe the same action of choosing k people from a group of n, they must be numerically equal. So this shows that the expression is indeed true. So this is an example of a more logical, or I guess like counting one thing in two different ways approach to counting, which I think is a very cool, it's a little bit different way of approaching a problem that you might not be familiar with. So I just want everyone to be a little bit more open-minded to it. And this kind of logical reasoning does carry over to problems in like easier, harder. It's kind of like you'll see this a lot in any level of math competition, essentially. Just be able to think about a situation from many different perspectives. Okay, so I know this is like probably a little bit complicated, a little bit maybe novel. So if you have any questions, please do ask. There will be another example of this kind of method, this kind of approach to solving or proving a statement later. So again, please try to understand. If you don't understand, please ask. So yeah. Any questions, comments, concerns? All right, well, let's move on then. Just want to the next thing, which is this pretty interesting identity. So if you look at the triangle and just add up all of the numbers in each row, right? What do you get? A very suspicious sequence of numbers, wouldn't you say? It looks like it's just the powers of 2. And so we have this identity that states that the sum of every row in this triangle is always a power of 2. And so there are multiple ways to approach this. I think that the way that you might be, I guess, might first try, and it does work, is just to use something called induction. This is more geared towards writing proofs, and I guess this is more of a higher level thing, but I think it's good to kind of understand, grasp the concepts a little bit earlier, especially since induction, recursion, that kind of thing is pretty prevalent. So, okay, so induction is essentially saying that you can generalize a statement or generalize a mathematical statement if you have something called the base case and an inductive step. And these are some really fancy terms for saying that your initial or your like easiest case, so the first row is always true, and that's obviously true because 2 to 0 equals to 1. And inductive just means that you can go from what you know is true to show that the next row is also true. The next statement is true. So essentially what that means is that if we know that this nth row here sums to equal to 2cn, then if we know this is true, then it implies that the next row sums to 2cn plus 1. And so I guess, can someone, I guess, explain, just I can type in chat, you can try to like say with your microphone, how might we show that each row is double of the next row? The sum of each row is double of the next row. What property of this triangle, by definition, allows or forces this to happen? Let's think about it this way. How can we determine, let's say this is the last row that we know. How can we determine what the numbers in this next row here, how can we determine what these numbers are going to be? How do we find these numbers?
You just add the ones above it.
Yep, that's by definition how the triangle works, right? And also notice that the ones on the ends carry over like this as well. So what if instead of writing the sum of each of them as just a single number, what if we wrote the sum as just like something plus another number? Like, for example, this is 1 plus 10. This number is 10 plus 45. This next number is 45 plus 120. I can't fit this all on the line. So let's keep on like this. What observations can you make about the numbers in this row and the numbers in this row, the next row, that up here? Okay, well, essentially, each of the numbers in this 10th row here, 1, 10, 45, for example, they appear twice when you add them in the next row. So this 1 goes to the 1 on the very left and goes to this number right here. The 10, you see there's a 10 here and another 10 like here. Same with the 45s, and same with like the 120, which I did not write. And you'll see that this applies for every single number in the row above it. So what this means is that each number in this 10th row contributes twice to the next row. So this directly implies that the next row would be 2 times that of the previous row. And since we know that the previous row must be a power of 2, then the next one must also be a power of 2. And that's how we can derive this expression. Okay, this is the pretty straightforward way. I guess the other approach would be to do this counting in 2 different ways that I talked about earlier. And I think this is a pretty good exercise as well. So what does, so this at this time, it's easier to start on the right-hand side. What does this even mean? This sum of n choose 0, n choose 1, n choose 2, all the way to n choose n. I'll just say right now, it's if you have n people, it's a number of ways to create, to choose a group of any number of people. So this is number of ways to choose 0 people, 1 person, 2 people, etc. So essentially, this is every possible group size and the number of ways to choose every possible group size. So that would mean that that's every possible way to choose a group of any size. Okay, so now, can anyone think of a way to relate what I just said about the right side to left side? How does the left side describe how to choose a group of any size from n people? Yes, that is a very, very nice. 2 choices in a row. If we think about each person, right? Think about them individually. So let's say like person 1, person 2, all the way to person n. They can either be in the group or not in the group. Those are 2 options. Those are the only 2 options. And so you have 2 options for all n people. So it's simply just 2tn total ways. And that's just another way to think about equating these 2 sides. All right, any questions? Okay. Okay, well, thanks for bearing through this part of Pascal's triangle. I just hope that it proves to be somewhat interesting and eye-opening, whatever, to at least one person. So hopefully it inspires you to do it. Okay. Yes, I know there are 10 minutes left. So on to our actual problems that I think everyone should try right now. And this method is called stars and bars, which we'll get into after we solve the problem. So if you have 4 identical pieces of candy, how can I distribute them? How many ways can I distribute them to an bottom counter? And here the only thing that matters
Are we supposed to do it, or are you going to explain it?
I guess I can explain this one because there are few similar ones right after this.
Too late, sent the problem answer already.
I see. Okay, well, let's walk through this. the only thing that you need to consider here is, I guess everyone who did. No, oh, never mind. The only thing we have to consider here is just how many each person gets, right? And I guess the main method of stars and bars is to consider what you're distributing as, well, stars. This is why it's called stars and bars. I mean, I don't think it's very efficient to draw them all, but we are. And bars. So essentially, like, we consider an arrangement of these objects as describing a distribution. So every unique arrangement of this is a different way to distribute your candies. So the bars here represent dividers between the three people. I'll call them A, B, and C. And then the number of stars within each separate like space separated by the bars refers to how many each person gets. So in this case, Anne gets 2, Bob gets 1, and Catherine gets 1. And so this is simply just 6 choose 2 because you have 6 spots to order the, I guess, objects or symbols, and you only need to choose 2 spots for where the bars go, and the rest will go to the stars. So the 6 choose 2, which is 15. All right, this is a pretty powerful tool to solve these problems where you have identical things, indistinguishable things from each other. All right, so if you have any questions, please ask. If not, we'll go on to, okay, the answer 15. So here's a suspiciously similar problem. Why don't we just have a go at it? All right. So to everyone who got it, good job. I guess the main thing I didn't talk about in the earlier problem was how to know how many number of bars to have. It's simply just a number of different like categories or people you can split it to. So in this case, there are 4 minus 1 because with 3 bars, for example, you have 4 different areas representing the 4 different people that the candy ends up at. And so we have 3 bars and we have these 12 pieces of candy. So like 12 stars and 3 bars. And so 12 plus 3 is 15. And we just need to choose 3 spots for all the bars. So this is just 15 choose 3. And this is 15 times 14, 13 over 3 times 2. Because the other factorial terms cancel out from the formula. And so this is just a pretty simple calculation. 15 divided by 3 is 5. 14 divided by 2 is 7. So this is 5 times 7 times 13. And final answer is 455. All right. So yeah, that was, I guess, pretty straightforward stars and bars. So I hope you understand. I'll talk more about this. I'll talk more about this when we restart the meeting. So. Okay, well, we'll talk more later. See you very soon.
Goodbye. There's less than a minute.
Yeah. Okay. I'll see y'all very soon. All right, so if you have any questions on the last problem, you can ask them now. So yeah, otherwise we'll move on. Okay. Next one. So try it out. Talk soon. Okay. Very surprisingly, this is a stars and bars problem. So it's just slightly hidden. Okay. So essentially, the first step is to take into account the constraint that each one has to have at least 1 pencil. So essentially, you can just say that everyone starts off with 1 pencil. So you just minus 3 from the total. So now you only have 3 pencils to split among 3 people because each of them already has to have 1. And so that means that there are 3 pencils and 2 bars because of 3 minus 1 is 2. So it's just 3 plus 2, choose 2. It's 5, choose 2, and that goes to 10. All right, so this is an actual AMC 8 problem from like, I don't know when, but yeah. Any questions, please ask. Otherwise, we move on. Okay, this next one, it's a bit long, but it should be kind of a review from last class. So this is also an actual problem. So yeah, nice. Keep breaking. I'm just gonna draw a diagram. All right, well, I guess it's a good thing that I put this problem in. So this problem is very, very similar to the stuff that I kind of talked about last class, where let's say if you wanted to go from a place, let's say we're in a 3x3 square, and you want to go from point A to point B, and you can only go in, as it says, the closest possible path, right? The shortest possible route means you can only go up and to the right. So there are 3 up motions, I guess, and 3 things going to the right. And so the number of ways is just 6 choose 3, or 3 plus 3 choose 3, or you have the string of ups and rights corresponds to a single path on this grid. And so that would equal to be 20 in the case of the example, right? So that was kind of that's kind of the idea behind this problem. And so if we take a look at this question, first thing you notice is that the park is kind of useless. It's just a little bit of a distraction in that you know that she takes a diagonal path through it. So there's only one path through the park. So I guess I kind of erased the sort of lines that I drew that might have been a little bit confusing. So that there's only one way to go from this southwest corner of the park to the northeast corner. And it's shown here in the diagram. So this is essentially just 2 parts. The first part from the house to the park, and the second part from the park to the school, right? And so this is a 1x2 grid. This is a 2x2 grid. So what would be the number of ways to go from house to park and from park to school? What would those numbers be? Well, I'll just say that there are 3 choose 1 and 4 choose 2, because this one is up, 1 up and 2 rights. So there are 3 total like movements, and you only need to choose 1 spot for where the up is. That's 3 choose 1. And from the one up here, you have 2 ups, 2 rights. So 4 total, and you only need 2 spots for the 2 ups or the 2 rights. And you multiply them together because these 2 sections are independent from each other. So for every path, for each of the 3 paths from the house to the park, there exists 6 different ways you go from the park to school. So that's why you multiply them, and so it's just 18. All right. So I sure hope that for those of you that did not get this, that you, I guess, refresh your memory from last class and understand how the method works again, and hopefully that you understand the solution to this problem, because this is a pretty common type of problem to be in the contest, so get used to that. Also, I think I might try to go back and show the exact problem that this is kind of very similar to that we went over earlier. So give me a minute. It's if anyone remembers this problem, it is almost identical in method to this. So yeah, just to refresh your memory, and we'll move on. Okay. So, Okay. Okay, well, this is the last problem. This is slightly different from all the other ones that we've done, but I kind of wanted to step through a more counting problem, just a straight up counting problem. All right, so just try to work it out. All right, so this is a pretty difficult problem. I will just start now so we can finish on time. So far, no one has the right answer. Okay, so this type of problem, you can think of it as, or this is generally classified as a casework problem. So what casework is, what it means is that you have to do a lot of work to count everything, and that's not always fun, but you have to do it. So this first part, case, means you think of different like scenarios that can occur, and work means you figure it out for each of the scenarios. All right. So when you have this kind of problem, you usually want to narrow down, start from like the most restricting condition and go down, right? So I think this one is 5 is the largest digit. This means both this and that they have 4 different digits. So first, you know that your digits can only come from 5, 4, 3, 2, 1, or 0. These are the only digits less than or equal to 5, right? And you must have 4 different ones. This means that you can't repeat any single one when you choose your number, essentially. And so let's just define our cases. So our first case is that, and now you think about what can you even do cases on? What different scenarios are there? And I think that use the last piece of information here. Integer is a multiple of 5. And if an integer is a multiple of 5, that means it ends in a 5 or 0. So for case 1, let's just say 5 is the last digit. So if this is the case, then our number is just like three digits and then a 5. So first, we know that none of these 3 digits can be a 5 because 5 is already used in the last spot. And next, we know that 0 can't be in the first spot because the leading digit is not 0. All right, so the easiest way is just to go through each place and just say how many different numbers can be there, right? So in the first spot, we have 4, 3, 2, or 1. They can all be in the first digit. There's nothing wrong with that. And then now, after one of the 4 digits has been put in, then we know that there are 4 more options for the next digit because let's assume like we chose 4, 3, 2, 1, and 0 are all options because this is no longer a leading digit, so 0 can be used. And now there are simply 3 choices remaining for our last slot since we've used 3 digits already, so there can only be 3 left. And so this is simply just 4 times 4 times 3, or 48 for the first case. And I do want you to notice that this is very similar to how you would calculate a permutation for like if you have like the numbers 1, 2, 3, 4, 5, and you want to put them in order in any random order, then it's 5 times 4 times 3 times 2 times 1. So it's kind of the same idea of going through each spot in like the number and just considering how many different choices there are. All right, we're going to go a little bit over time. And our next case is that 0 is the last digit. And with the cases, you have to make sure that they cover all possible situations. And I think it's pretty clear here that these 2 cases cover all possible scenarios since they can only end in 0 or 5, as it's also 5. Right. So if 0 is the last digit, I'll move this here. It's going to look something like this: 3 digits and a 0. Right. How many options are there for this first number now? Actually, no. I think that it's something before this. Since 5 is not the last digit here, that means that 5 must be one of the 3 digits here because 5 is the largest digit, implies that 5 is a digit in the number, right? And notice that since 0 is already at the end, we don't have to worry about any zeros in the leading digit spot, so we can kind of ignore that problem. So with that being said, since there is a 5 in this number, and there are 3 different options for where the 5 is, then let's just assume that the 5 is here. It doesn't matter. And we'll just have this 3 and denote the number of places put the 5. Right, so now we have 2 spots left. How many different digits options do we have for this first one? You can say it out loud, type in the chat, whatever. How many options do we have? You can't use the same digit twice, and these are the only digits you have as options to use, and you can't use 5 or 0. How many options do we have for this first digit? Right, it's 4. There are 1, 2, 3, 4 different numbers remaining. So we have 4 choices for the first one. And now how many are available for the second slot, now that we've already chosen one for the first slot? Well, it's 3. And that's because now that you have a number here, this eliminates one of the remaining numbers. So 3 times 4 times 3. This is the 3 representing the last slot. And so this equals 36. And now at the end, what do we do with these last 2 numbers, 48 and 36? Do we add them? Do we multiply them? What do we do? That's right. We add them to 84. And as you can see, the answer is 84. The reason why we add them is because these are cases. They're kind of like, they're separate, but like they all count like end results, and they're not like, you don't multiply them together because you're not like trying to form like a 4-digit number from like the two parts. They're already fully formed, as you can think. So you just add them, okay? And this is usually the last step of casework, where you add up everything so you make a final solution. Here's 84. All right. So I hope that that was a good introduction, or I don't know, exposure to a counting problem in this sense, and I guess a method that you would use to approach it. If there are any questions, please ask. You can find this exact problem online on AOPS. I don't know what year it is or anything like that, but I'm sure you can type it in and find it, or you can use this method. This is the solution. So if you don't have, if you do have any questions, you can email me to ask right now, whatever. If you don't, hope you enjoyed this class. If you didn't enjoy this class, well, hope you'll still show up next time. Anyway, that's it for the class. So take care, everyone.
Thank you.
See you next week.
Bye.